I hope everyone's doing well. I am Mr. Ish. Thank you for joining me for this video. It's an interesting video here with regards to determining the area of any inscribed polygon in a circle having n equal sides. And it's represented as this area with a subscript n representing the number of sides in that polygon. Area that is dependent on the number of sides. Look right here, a circle. Here n is equal to 3 because there are 3 equal sides. Look at this representation. I have a circle here in which I have a square. N is equal to 4, and these are regular polygons having equal sides. And look at this representation. What we can do over here is draw a hexagon, a regular hexagon with 6 equal sides, and then you can see this to be the case. What you will understand and realize is that as these n values become larger and larger and they tend to go towards infinity, this inscribed polygon becomes more and more, and actually it becomes a circle. As you're inscribing polygons with more sides, it's becoming a circle. The representation here, what we're trying to determine is what are the areas of these polygons, because they're dependent on the number of sides. And everything stems from this geometric idea that from the center of each of these you can start drawing equal triangles. When you separate them out into these individual triangles, and each of these represent a number of triangles that's equal to the number of sides. Here n is equal to 3, I'm generating 3 triangles. Here n equals 4, I'm generating 4 triangles. N equals 6 triangles. And this is the center in all of the cases. And in all of these cases, these are representing the radius. And you can see it to be the case, radius, because the center is being connected to the vertex or the vertices of these inscribed polygons, and those segments are radii. And then you're seeing internal angles being generated. All of these internal angles are dependent on the value of that n, which is the number of sides. If a full revolution is 2 pi, then you would have here as your angle, each of these angles would be 2 pi over n. Here would be 2 pi over 3, here would be 2 pi over 4, here would be 2 pi over 6. As the number of sides increase, the angles become smaller, and the number of inscribed smaller triangles, each of which are equal to each other, become more and more. So, but what is the overall area of these polygons? And that's what we're determining, and we can do it very easily using a general representation. Our representation will depend on this one right here, using a triangle, but it's just as good if I'd used any other polygon. When you're looking at this triangle, you can pluck it out and it looks something like this. You know there's a center of the circle, it represents here, and then you're generating these radii. And as I've told you, you're splitting each of these inscribed polygons into equal number of triangles, which is equal to your n value, the number of sides. Here I have 3 triangles, I have 3 sides. And yeah, just look at one of these triangles and pluck it out right over here. This right here is this. If I can determine the area of one of these, all I have to do is multiply that area times the number of n triangles, and I'll have my area n, which is exactly this what I have. I've already told you that there's a certain angle over here, internal angle, that theta is equal to 2 pi over n. I can split it up. I have a certain base over here, I have a certain base over here, I have a total base over here, and then I have a height. This right here is representing that. I can just pull out one of these triangles and I can draw it out over here for you. There's a base over 2, there's a certain angle, 90 degrees, there's a certain radius. These are my radii right here, as you can see. A certain height. What is this angle right here? This angle represents half of that angle, because this angle is theta is 2 pi over n. If you divide it by 2, you have 2 pi over 2n, which is equal to pi over n. So this angle right over here is pi over n, which means this right here is the complement, which is 90 minus pi over n, and that's what it will be. So what we will do is just utilize this. If I can determine from here the area of this triangle, I'll multiply it by n and get my area of that inscribed polygon, and it's not too hard. To do this, remember your cofunction identities. The sine of an angle in terms of 90 minus theta is always equal to cosine of its complement, or the cosine of 90 minus theta is equal to sine of its complement, because we will utilize that. Now I want to determine the height. I can do sine of this angle, sine of 90 minus pi over n. Remember this right here, angle right here was 2 pi over n. When I bisected it, I'm dividing it by 2, it becomes pi over n, which is right here. Then its complement is 90 minus pi over n. This right here, by means of cofunction identity, is equal to cosine pi over n, which is equal to what? The opposite, height over r. I'm solving for h, and I see here h is equal to, you push this on the other side, r cosine pi over n. So that's one item done. From the same triangle, I have a cosine. Cosine of this 90 minus pi over n is equal to adjacent, which is b over 2, divided by the hypotenuse r, which is equal to b over 2r. But bring in the cofunction identity. This right here is equal to sine pi over n, which is equal to b over 2r. And solve for b. You push this on the other side. You have a 2r sine pi over n. And we'll put that here. b is equal to 2r sine pi over n. Now a very good thing happens. You see how here we were looking at b over 2, but here I've calculated b. By looking at just b over 2 and then this whole procedure, I found the entire length. So we're great. We've determined the entire length of the base. We don't even have to multiply by 2. We already have the times 2 here coming through automatically. We have everything now to determine the area of this triangle. The area of that triangle is equal to base height over 2, and I have base, which is 2r sine pi over n, times my height, which is r cosine pi over n, divided by 2, which is this. This cancels out with this. The r's combine. You have area is equal to r square sine pi over n and cosine pi over n. Now think about a very fundamental trigonometric identity, which is your sine double angle. Sine 2 theta is equal to 2 sine theta cosine theta. But if I push the 2 onto the other side, I'm really looking at sine 2 theta over 2 is equal to just sine theta and cosine theta, and that's exactly what I have right here. I have just sine theta cosine theta, and I can bring in this right here for this part right here. So area will be equal to r square, and the 2 can be attached to this radius square, and I'm looking at a sine 2 theta, and where theta is equal to pi over n. This right here represents the area of all of this. All I have to do is multiply it by n, because there are n number of triangles given whatever inscribed polygon here we would be looking at. Here we're looking at 3, you would multiply by 3. But we're keeping it general because we're trying to determine a generalized formula for an inscribed regular polygon in a circle, and your answer would be multiplying with the n. It would be n r square over 2 sine 2 pi over n, and that represents this right here, and I'll bring it for you over here. The area of any regular polygon inscribed in a circle is always equal to n r square over 2 sine 2 pi over n. Let me close with a very interesting fact for you all. We have come to this formula where the area of any inscribed polygon having n equal sides is equal to nr square over 2 times sine 2 pi r n, where n is considered to be a finite number of sides. However, if n were to approach infinity in inscribed polygon with an infinite number of sides, then this an, you can use calculus to show it, but I won't show it to you in this video. But this is just an extra fact. This right here, this entire formula would become pi r squared, the area of a circle. So this right here, if n were to approach infinity, would become pi r squared. And if anyone is interested, they can ask me in the comment section, and I can guide them as to how you can show this. This right here is our formula we've derived, but as n approaches infinity, the inscribed polygon becomes a circle, the area becomes pi r squared. And with that, we end this video. Thank you.